Welcome to This Explainer. Today, we're diving into what I can only describe as a real-life medical detective story. We're looking at some truly cutting-edge research on using eye scans and artificial intelligence to catch dementia earlier than ever before. It's this perfect blend of biology, optics, and deep learning. And honestly, the implications for global healthcare are absolutely massive. Here is our roadmap for today. We'll cover the dementia detection crisis, look at the eye as a window to the brain, explore seeing the invisible, see what happens when deep learning meets eyes, review the AI diagnostic results, and finally, look at the future of screening. Let's jump right in. 55 million. We've got to start with this staggering number because it really sets the stakes for everything we're about to talk about. Right now, there are over 55 million people worldwide living with dementia. It's a massive, rapidly growing global health crisis, and get this, that number is projected to nearly triple by the year 2050. It's a daunting reality, and researchers are absolutely racing against the clock to change it. But there is a glimmer of hope. Recent reports suggest that up to 45% of dementia cases could potentially be delayed if we just addressed the risk factors early enough. Because of this, researchers started asking a pretty bold question. What if the ultimate early warning system is actually a simple eye scan? Section 1. The Dementia Detection Crisis. Section 2. A window to the brain. You know, the real villain in this story isn't just the disease itself. It's the fact that late detection steals so much valuable time. By the time someone starts noticing memory loss, significant structural damage in the brain has usually already happened. We desperately need a way to detect those biochemical changes much, much earlier. And this is exactly where the retina comes in. Because the retina develops from the exact same embryonic tissue as the brain, it acts like the perfect crime scene for early clues. It is literally an extension of your central nervous system. This gives us a front row seat to neurodegeneration without needing any invasive surgeries or incredibly expensive, heavy machinery like a PET scan. But of course, there's a catch. Standard color cameras, the kind your eye doctor uses to take those standard retinal images, well, they capture the basic structural details, but they completely miss the invisible biochemical fingerprints of the disease. Standard RGB imaging just doesn't have the sensitivity to pick up on the subtle buildup of disease-causing proteins, and that is precisely why we need a better tool. Section 3. Seeing the invisible. So, enter hyperspectral imaging, or HSI. Think of this almost like a UV light at a crime scene. Instead of just capturing the standard red, green, and blue light, it pulls in a massive data cube made up of 401 different bands of the visible light spectrum. Why on earth do we need all that extra data? Well, a major target in Alzheimer's disease is the toxic amyloid beta protein. When light hits these toxic proteins in the retina, they actually scatter that light in very specific ways. It's kind of like how you see dust particles catching and scattering sunlight in a dark room. The smaller protein clusters cause what's called Rayleigh scattering, and the larger plaques cause Mies scattering. HSI is actually sensitive enough to detect those unique optical signatures. How cool is that? Now, what's really fascinating here is the stark difference we see when we look at the longer wavelengths, specifically the 600 to 780 nanometer red and near-infrared range. The researchers looked at 5 different regions of the retina and found that in the shorter wavelengths, between 380 and 550 nanometers, the eyes of healthy folks in dementia patients looked pretty much identical. But in these longer ranges, there is a significant, progressive increase in light reflectance as a patient moves from normal cognition to mild impairment and then to full dementia. Basically, the disease leaves a glowing spectral footprint. Section 4. Deep learning meets eyes. Now, human eyes obviously can't naturally read a 401-band hyperspectral data cube. So, to make sense of all this invisible data, the researchers brought in some brilliant digital detectives. In a meticulously designed study of 137 participants, they followed 3 really elegant steps. First, they captured over 3,200 standard eye photos. Then, using some highly advanced mathematics, they essentially digitally reconstructed those flat images into high-fidelity 3D hyperspectral cubes. Finally, they fed this incredibly rich spectral map into deep learning AI models to see if the computer could spot the hidden patterns of dementia. And they didn't just stop at one model either. They unleashed 4 state-of-the-art convolutional neural networks on this data. These are AI architectures specifically built to recognize complex visual patterns. The ultimate goal? To see if the AI could accurately sort patients into 3 distinct categories based on their clinical cognitive scores: normal control, mild cognitive impairment, or dementia. They trained the AI on both the standard RGB images and the newly created hyperspectral images just to compare the results directly. Section 5. The AI Diagnostic Results. So what happened? Well, the results are incredibly promising. When they swapped the standard color images for the hyperspectral data, the AI saw an immediate accuracy boost across the board. Resonant 50 actually led the pack, hitting an impressive 84% overall accuracy in categorizing the patients, up from 80% on standard images. GoogleNet and EfficientNet followed really closely behind. The extra layers of data from the hyperspectral reconstruction genuinely gave the AI the deep context it needed to make significantly better diagnoses. But right here is the absolute aha moment of the research. You see, diagnosing full-blown dementia is one thing, but catching mild cognitive impairment, or MCI, is notoriously difficult because the physical signs are just so incredibly subtle. When looking at standard images, the Resonant 50 model could only identify MCI cases about 63% of the time. But when they gave it the hyperspectral data, that ability skyrocketed to 81%. That is a massive leap. And this highlights exactly why those invisible wavelengths matter so much. They allow the AI to catch the subtle, early-stage signs of decline that standard RGB images simply do not have the raw data to show. Catching a patient during this MCI phase is essentially the holy grail of dementia care. Why? Because that is the critical window where lifestyle interventions, risk factor management, and emerging therapeutics can actually alter the course of the disease before it's too late. Section 6. The future of screening. Now, to be totally objective here, the researchers are careful to note that this isn't a final, standalone diagnostic tool just yet. It definitely still requires broader external validation across different hospitals and patient demographics. However, it holds unbelievable promise as an early warning checkpoint. Just imagine going in for a routine eye exam, and a non-invasive, highly cost-effective algorithm flags you as a high risk right then and there. This would allow your doctor to intervene way before you ever need an expensive, invasive neurological evaluation. It's a really profound thought to end on. By combining the biological window of the retina, the physics of hyperspectral light scattering, and the sheer pattern recognition power of deep learning, we're standing right on the edge of a diagnostic revolution. It really leaves us to wonder, how many millions of minds might be protected, and how many families might be spared the worst of this disease once this AI detective fully enters the clinic? Thank you so much for joining me for this explainer, and keep your eyes open for what the future holds.